Welcome to this coding walkthrough. Today, we'll be tackling problem number 2206, titled Divide Array into Equal Pairs. This problem challenges us to think critically about how to group elements in an array efficiently. Let's dive into the details and explore the solution step by step. In this problem, you are tasked with dividing an integer array, nums, into pairs. The array is guaranteed to have an even length, specifically 2*n, meaning there will always be an even number of elements. The goal is to determine if it's possible to group these elements into exactly n pairs, where each pair contains two numbers that are equal. Additionally, no element should remain unpaired after forming these pairs. If this is achievable, you return true, otherwise, return false. The input is an array of integers with a length between 2 and 500, and each element in the array falls within the range of 1 to 500. The output is a Boolean value, true or false, representing whether the required grouping is possible or not. Let's explore some concrete examples to better understand the problem requirements. Consider the first example, where the input array is nums equals 3, 2, 3, 2, 2, 2. In this case, the output is true. This is because the array can be divided into three valid pairs. The first pair is 3, 3, the second pair is 2, 2, and the third pair is 2, 2. Importantly, each pair contains two equal elements, and no elements are left unpaired. Since the conditions are met, the result is true. Now, let's take a look at another example to see how the output changes when it's not possible to form such pairs. In the second example, the input is nums equals 1, 2, 3, 4. Here, the output is false. This is because there is no way to divide the array into pairs such that each pair contains two equal elements. None of the numbers in the array appear more than once, so it's impossible to form any valid pairs. For example, attempting to group 1, 2, or 3, 4 would not satisfy the condition that both elements in a pair must be equal. Therefore, the result is false. Now, let's examine another example where the conditions are successfully met. In the third example, the input array is nums equals 10, 10, 20, 20, 30, 30. The output here is true because the array can be divided into three valid pairs. The first pair is 10, 10, the second pair is 20, 20, and the third pair is 30, 30. Once again, all pairs contain two equal elements, and no numbers are left unpaired. This satisfies the problem's requirements, so the result is true. Some constraints to keep in mind include the fact that the array length is always even, and all elements fall within the range of 1 to 500. Key edge cases include arrays where all elements are unique, which will always return false, or arrays where all elements are identical, which will always return true. Additionally, if any element has an odd frequency, it will be impossible to form pairs, and the result will be false in such cases. To begin with, let's consider a brute force approach to solve the problem. The idea here is to identify all possible pairs of elements in the array and check if each pair contains two equal elements. This would involve iterating over the array, trying to pair each element with another, and removing paired elements from the array. The process continues until either all elements are successfully paired or it becomes impossible to do so. However, this approach is computationally expensive. One key observation is that for pairing to be possible, the array must have an even frequency of each number since each pair requires exactly two of the same element. The drawback of this method is its inefficiency for larger arrays, as the time complexity grows quadratically with the size of the input, making it impractical for large datasets. Now, let's shift our focus to an optimized approach using a hash map. The key insight here is that for the array to be divided into pairs of equal elements, each number must have an even frequency. For example, if the number 3 appears 4 times, it can form two pairs of 3, 3. But if any number appears an odd number of times, forming complete pairs becomes impossible. Using a hash map, we can count the frequency of each number in the array efficiently. The process involves three main steps. First, creating a hash map to store the frequency of each number. Second, traversing the array to update the frequency counts. And finally, iterating over the hash map to verify if all frequencies are even. If any frequency is odd, we return false, otherwise, we return true. This systematic approach ensures that we can quickly determine whether the array can be paired as required. The hash map approach offers several advantages. It allows us to count the frequencies of elements in O(n) time, which is far more efficient than the nested iterations required in the brute force method. Additionally, checking if all frequencies are even involves just one more pass through the hash maps keys, making it computationally inexpensive. In terms of time complexity, this approach operates in O(n) due to the linear traversal of the array and the hash map. The space complexity is O(k), where k is the number of unique elements in the array, as the hash map stores only these unique counts. This strategy was chosen because it is both time efficient and conceptually straightforward to implement. While it does require slightly more memory to store the hash map, this trade-off is easily justified by the significant reduction in runtime complexity, making the solution scalable to larger inputs. The key breakthrough in this problem was realizing that we don't need to explicitly form pairs to determine if the array can be divided. Instead, the problem boils down to checking the parity of the frequencies of each number. This insight simplifies the implementation significantly, as we can rely on a hash map to track frequencies and eliminate the need for more complex operations like nested iterations or manual pairing. By focusing on frequency counts and their evenness, we achieve both an elegant solution and a dramatic improvement in runtime performance. This shift in perspective highlights the power of leveraging problem-specific observations to optimize computational strategies. In this problem, we aim to divide an array into pairs of equal elements. Once we identify a pair, we remove those elements from the array and continue searching for more pairs. Our ultimate goal is to determine how many such pairs can be formed. To approach this, we'll start with a straightforward brute force method. First, we initialize a variable, count, to track the number of pairs. Then, we use a loop to iterate over the array, systematically comparing elements to find matches. The process begins with an outer loop that selects each element in the array as a candidate for pairing. The index of the selected element is denoted by I, and this ensures every element gets a chance to be evaluated. Next, for each selected element, we use an inner loop to compare it with every subsequent element in the array. These subsequent elements are indexed by j, where j is always greater than I. If we find two elements that are equal, we've identified a valid pair. When a pair is found, we increment the count variable to register that pair. Then, both elements forming the pair are removed from the array to ensure they are not considered in future comparisons. However, it's important to note that directly removing elements from an array can be computationally expensive, as it requires shifting the remaining elements to maintain order. This step can add to the overall time complexity of the algorithm. We repeat this process of selecting elements, comparing them, and removing pairs until all elements in the array have been processed. At this point, no more pairs can be formed. Finally, the value of count represents the total number of pairs that were identified and removed from the array. This value is then returned as the result of the algorithm. The brute force approach, while simple to understand, involves comparing each element with every other element, leading to a time complexity of O(n) squared, due to the nested loop structure. Additionally, the process of dynamically removing elements adds further computational overhead. For instance, when elements are removed, the array must adjust its indices, which can be costly. It's also essential to consider specific edge cases. For example, if the array contains no duplicate elements, the loops will complete without identifying any pairs, resulting in a count of 0. On the other hand, if all elements in the array are identical, every element can be paired, and the total number of pairs will be the floor of n divided by 2, where n is the size of the array. In the case of an empty array, the algorithm should return 0, as there are no elements to process. The data structures used in this approach include the input array, which stores the elements to be paired, and the count variable, which tracks the number of pairs formed. The key operations in this algorithm include pair checking, element removal, and iterating through the array with nested loops. Pair checking ensures that duplicates are identified accurately by comparing each element to every other element. Removing paired elements allows the algorithm to focus only on the remaining unpaired elements, simplifying subsequent iterations. The nested loops, while ensuring correctness by evaluating all possible pairs, come at the cost of efficiency. Since this brute force method is not optimal for large arrays, it's worth considering potential optimizations. For example, using a hash map to count the frequency of each element could significantly reduce the time complexity to O(n). This approach avoids the need for nested loops and element removal, making it a much more efficient solution for larger datasets. To better understand how the brute force approach works, let's walk through an example. Consider the input array 1, 2, 1, 2, 3. We start by initializing count to 0. The outer loop first picks the element 1 at index 0, and the inner loop finds a match with another 1 at index 2. We increment count to 1 and remove both ones from the array, leaving 2, 2, 3. The outer loop then picks the element 2 at index 0, and the inner loop finds a match with another 2 at index 1. We increment count to 2 and remove both 2's, leaving 3. At this point, no more pairs can be formed, and the algorithm returns count equals 2. In terms of complexity, the time complexity is O(n) squared, due to the nested loops, while the space complexity is O(1), as no additional data structures are used beyond the input array. This solution uses a straightforward approach to determine if the given array can be divided into pairs of equal elements. Let's break it down step by step. 1. Importing counter. The collections counter is imported to count the frequency of each element in the array efficiently. This avoids manually iterating through the array to calculate frequencies, making the code cleaner and faster. 2. Counting frequencies. The counter nums function is used to create a dictionary-like object where the keys are the unique elements of the nums array, and the values are their respective counts. For example, if nums equals 1, 2, 2, 1, 1, 1, then frequency would be 1, 4, 2, 2. 3. Checking pair formation. The code iterates through the values in the frequency object, i.e., the counts of each element. If any count is odd, it returns false immediately because it's impossible to form pairs with an odd number of elements. For instance, if an element appears 3 times, one of those occurrences cannot be paired with another. For returning true, if the loop completes without finding any odd counts, the function returns true. This means all elements in the array have even frequencies, allowing the array to be divided into pairs. ###key details. The time complexity of this solution is O(n), where n is the length of the array. This is because counting the frequencies using counter takes O(n), and iterating through the frequency dictionary is O(k), where k is the number of unique elements, k less than or equal to n. The space complexity is O(k), as we store the frequencies of unique elements in the frequency dictionary. ###example. Input, nums equals 3, 3, 2, 2, 1, 1. Frequency equals 3, 2, 2, 2, 1, 2. All counts are even, so the function returns true. Input, nums equals 1, 2, 3, 4. Frequency equals 1, 1, 2, 1, 3, 1, 4, 1. Some counts are odd, so the function returns false. This implementation is optimal, concise, and handles all edge cases effectively. This is the Java implementation of LeetCode problem number 2206, divide array into equal pairs. It mirrors the Python solution by using a hash map to maintain the frequency of each number in the array. The solution then checks if all frequencies are even, returning true if the array can be divided into equal pairs, and false otherwise. This implementation highlights Java-specific differences such as explicit type declarations, the use of hashmap for counting, and enhanced for loops for iteration. To solve this problem, we begin with the array nums equals 3, 3, 2, 2, 1, 1, and input it into the divide array function. The first step is to compute the frequency of each number in the array using Python's counter from the collections module. This gives us a dictionary where the keys are the unique numbers and the values are their respective frequencies. In this case, the counter object outputs 3, 2, 2, 2, 1, 2, meaning that the numbers 3, 2, and 1 each appear exactly twice in the array. Next, we iterate through the frequency values, which are 2, 2, 2, and check if each value is even by verifying whether count%2 equals 0. For count equals 2, the frequency of 3, the modulus operation confirms that it is even. The same holds true for the frequencies of 2 and 1, all of which are also even. Since all frequencies satisfy the even condition, the function returns true, meaning it is possible to divide the array into equal pairs. The final output is true. Now, let's consider a different example with the input array nums equals 1, 2, 3, 4. Again, we use counter nums to calculate the frequency of each number. This time, the counter object outputs 1, 1, 2, 1, 3, 1 for 1, indicating that each number in the array appears exactly once. With the frequency values being 1, 1, 1, 1, we check each value to see if it is even by verifying whether count %2 equals 0. For count equals 1, the frequency of 1, the modulus operation shows that it is not even. Since at least one frequency is odd, it is not possible to divide the array into equal pairs. As a result, the function returns false. The final output in this case is false. In the last example, we use the input array nums equals 2, 2, 2, 2, 3, 3, 3, 3. Using counter nums, we calculate the frequency of each number, obtaining the counter object 2, 4, 3, 4. This tells us that the number 2 appears 4 times, and the number 3 also appears 4 times. Next, we iterate through the frequency values 4, 4, and check whether each value is even. For count equals 4, the frequency of 2, the modulus operation confirms that it is even. Similarly, for count equals 4, the frequency of 3, the result is also even. Since all frequencies are even, the function determines that it is possible to divide the array into equal pairs. Therefore, the function returns true, and the final output is true. To understand the time complexity of this solution for problem number 2206, we break it down into two main operations. First, we use the counter function from Python's collections module to calculate the frequency of each number in the input list nums. This step involves iterating through the list once, and since it processes each element exactly once, its time complexity is O(n), where n is the size of the input list. Next, we retrieve the frequency values using the frequency.values function and then iterate over these frequencies with a loop. Retrieving the values is a constant time operation, O(1), but the loop itself iterates over all unique elements in nums. Let's call the number of unique elements k. In the worst case, where all elements are unique, k equals n, so the loop also takes O(n) time. Within the loop, the conditional check to see if a count is odd, using count %2 equals 0, is an O(1) operation for each frequency value. This means the loop's overall time complexity is O(k), which is O(n) in the worst case. Combining these steps, the total time complexity so far is O(n) from the counter and O(n) from the loop, resulting in O(n) overall. Now, when we combine the time complexity of the counter operation and the loop over the unique frequencies, we get O(n) plus O(n), which simplifies to O(n). This demonstrates that the algorithm scales linearly with the size of the input list. Moving on to space complexity, the primary contributor is the counter object. This data structure stores a key-value pair for each unique number in nums. In the worst case, when all elements in nums are unique, the counter will store n key-value pairs, giving it a space complexity of O(k), where k is the number of unique elements. Again, in the worst case, k equals n, so the space complexity here is O(n). Additionally, the input list nums itself requires O(n) space, as it holds all the elements. Finally, the algorithm uses constant space for auxiliary variables such as the loop iterator in temporary variables, which is O(1). Combining these, the total space complexity is dominated by the counter storage, leading to an overall space complexity of O(n). Looking at the overall space complexity, it's clear that the counter object dominates due to its storage of frequency data, resulting in O(n) space complexity. To evaluate the efficiency of this optimized solution, let's compare it to a brute force approach. A naive method would involve iterating through the input list and manually grouping elements into pairs. This would require a nested loop, where for each element, the algorithm searches for a matching pair. In the worst case, this results in O(n) squared time complexity because every element might need to be compared with every other element. The space complexity for this brute force method would remain O(n), as we still need to store the input list. However, the optimized approach used in the solution avoids this inefficiency by leveraging the counter data structure to pre-compute frequencies in linear time, reducing the time complexity to O(n). Although the space complexity remains O(n) in both methods, the drastic reduction in time complexity makes the optimized approach significantly more efficient, especially for larger input sizes. Finally, let's analyze the algorithm under different scenarios. In the best-case scenario, where all elements in nums already have even counts, the algorithm still performs the counter operation and iterates through the frequency values. These steps ensure that the time complexity remains O(n). For the average case, the algorithm processes all elements and their frequencies, which still leads to O(n) time complexity. In the worst-case scenario, where all elements in nums are unique, the algorithm must process each element and its frequency. Even in this case, the time complexity remains O(n). This consistency arises because the counter operation and frequency iteration both scale linearly with the size of the input list, and there are no nested loops or recursive calls that would increase the complexity. As a result, the mathematical proof for the algorithm's time complexity confirms that it is O(n) for all cases, while the space complexity also holds steady at O(n), dominated by the storage requirements of the counter object. When tackling this problem, it's important to watch out for a few common mistakes. First, not considering edge cases like an empty array, arrays with only one element, or arrays where all elements are identical. Overlooking these scenarios can lead to errors or crashes in your code. Another frequent issue arises in brute force implementations, where candidates might mistakenly loop over the same indices twice instead of ensuring that pairs are evaluated correctly. This wastes computation and leads to incorrect results. Additionally, using inefficient data structures can severely impact performance. For example, tracking elements with a list instead of a set or dictionary increases time complexity unnecessarily. Space complexity is another factor to consider. Candidates sometimes use extra memory, like additional arrays, when in-place operations would suffice. Finally, hard-coding values, such as assuming fixed array sizes, reduces the flexibility and generality of your solution, which can be a major drawback. Now, in interviews, this type of problem often serves as a warm-up question, and it can come with variations. For instance, you might be asked to count unique pairs, handle absolute differences, or work with duplicate elements. Understanding these variations helps you adapt quickly. You should also consider the trade-offs between time and space complexity. For example, while a hash table provides fast lookups with O(n) time complexity, it requires additional space. On the other hand, a two-pointer approach may save space but could require sorted input, adding extra pre-processing steps. Interviewers appreciate when you start with a straightforward brute force solution and then optimize it step by step, showing clear incremental improvements. Also, make sure to communicate your thought process clearly. For example, explain why you're using a particular data structure, like a hash table, and how it supports your algorithm. This demonstrates both your problem-solving skills and your understanding of computational efficiency. This problem is also closely related to several other popular LeetCode problems, which makes practicing them extremely beneficial. For example, the two-sum problem asks you to find two numbers in an array that sum to a specific target, and it's a great way to practice hash table usage. The three-sum problem extends this idea, requiring you to find unique triplets that sum to 0, which often involves sorting and handling duplicates. Another related problem is k-diff pairs in an array, where you count unique pairs with a specific difference, testing your ability to handle variations in pair evaluation. Finally, contains duplicate is a simpler problem but emphasizes the importance of efficient data structures to quickly identify repeated elements. These problems share overlapping concepts, and solving them can help you develop a deeper understanding of pair-related algorithms and data structure trade-offs. To solve this type of problem, there are several approaches you can consider, each with its own trade-offs. The brute force approach, for example, involves comparing all possible pairs using nested loops. While this method is straightforward and easy to implement, it comes with a time complexity of O(n squared, which makes it suitable only for small input sizes. A more efficient alternative is the hash table approach, where you track elements as you iterate through the array. This reduces the time complexity to O(n), but it does require O(n) extra space, making it ideal for larger inputs. The two-pointer technique is another option, particularly if the input array is sorted. This method can achieve O(n log n, or even O(n) time complexity while using only O(1) space. However, it requires the array to be sorted, so you may need to account for the cost of sorting. Lastly, you could use sorting combined with binary search. This approach also has a time complexity of O(n log n, and can save space compared to hash-based methods, but it introduces additional complexity in implementation. Each of these techniques has its strengths and weaknesses, so the best choice depends on the specific constraints of the problem you're solving. Great job! We've successfully solved and reviewed the problem divide array into equal pairs. Remember, the key takeaway here is the effective use of hash maps for frequency counts. Keep practicing, and don't forget to subscribe to stay updated with more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!